Hi, everybody. I'd like to provide a three-part sort of setting the stage for our work that we'll do in class on Thursday this week. We spent a little bit of time Tuesday discussing the behavior of a coil as an inductor in and of itself, right? As a circuit device that responds to the passage of current with an EMF, to the change, right, in the current that it passes with an induced EMF. Consider a series circuit with a traditional EMF, a battery, a resistor, and an inductor, and a switch. At time t equals 0, we close the switch, and the question is, what happens? Now, we've got an EMF and a resistor. There should be some current, should instantaneously flow. But if we try to pass an instantaneous current through the inductor, we have changed the current infinitely fast, which means the induced EMF will be infinitely large, which will oppose the battery, and we won't actually get anywhere. So the current can't change instantly to some set final value. We have to change it gradually and build up the magnetic field storing energy by passing a constant current, a steady current through the inductor. So what we're interested in is the current as a function of time. We would like to get that result. What does it look like as the magnetic field is slowly built over time as represented by the current passing through the inductor coil? We are looking at this first, a RL circuit, a resistor and an inductor. After that, we'll look at a circuit with an inductor and a capacitor. And after that, we'll look at briefly, it's sort of, again, setting the stage for Thursday's activities, a circuit with all three, resistor, inductor, and capacitor. Now, if we were interested in an application of Kirchhoff's loop rule around this particular circuit, we need to know how to express the potential difference across each circuit element. Now, the battery is the easy one. As we go from point C through the battery to point A, after we close the switch, the potential difference of A relative to C is just the positive EMF of the battery itself. Straightforward. As we go through the resistor from point A to point B, the potential of point B, which is downstream in the current direction from point A, passing through the resistor means that we had to spend some of the work we had spent, we had been sort of given, and our potential at B is less than our potential at A. So in the current direction, in the Kirchhoff loop rule direction, we would represent that potential difference as a negative voltage. The voltage across a resistor is just the current, the instantaneous current, times the resistance. Now, as the current changes in this circuit, the EMF induced across the inductor from one side to the other, from point B to point C in the circuit, is proportional to its self-inductance and the rate of change of the current. Now, if the current is increasing in the indicated direction, clockwise, the inductor, the induced EMF is such that as we look at point C, it is down arrow. It's the opposite direction from the induced voltage. So if we wanted to represent the potential difference across the inductor as a result of the changing current through it, again, we would use a minus sign to account for Lenz's law and for the direction, I guess, of the induced EMF. Okay, so let's apply Kirchhoff's rule to this loop. Let's start at point C and go clockwise through the battery. Kirchhoff loop. First, we see the battery, then we see the resistor, and then we see and we should be back to square one by that point. A couple things to note. At time t equals 0, there is no current flowing yet. So there is no potential difference across the resistor yet, which means the initial rate of change right when we close the switch of the current in the circuit has to be the ratio between the EMF and the self-inductance, or just the inductance of the inductor. Later, much later, once we have reached a steady current, the rate of change of the current goes to 0. And our Kirchhoff equation becomes the traditional Ohm's law statement. It's like the inductor isn't even there, it's just a wire. It's carrying current, and if that current isn't changing, then there's no reason for there to be an EMF across the inductor for us to worry about. It's behaving just like any other piece of wire. Now, there is a magnetic field set up due to the current in the coil, and we have, as we saw on Tuesday, we are storing energy in that magnetic field. As long as we're passing current. All right, what if we're asking about a time in between? We have our general Kirchhoff equation, and this is a very similar equation to the equation we had back when we were talking about capacitors. We could separate variables. let's see. When we were working with capacitors, we had dV over V. So we'd like to end up in that kind of place. With our differential equation. So let's see, what's the most advantageous way to write this differential equation? We've got one way here. Another way might be but the trick is we'd like to get the current and its differential on the same side of the equal sign. EMF and R are just constants, so those can safely be part of the expression. And at this point, I think we can separate variables. That looks like an O. Fix that. On the left-hand side, we have constants and dt. On the right-hand side, we have constants and I and di. So we can integrate both sides, as we did back when we were talking about capacitors. The U substitution we need is going to introduce a negative sign, and I'd like to put that on the left-hand side of the equal sign. Officially, this should be a definite integral. We're starting from t equals 0 to some final time. And the current is linked by the original derivative di by dt. So we're interested in the current at time t final and the current at time 0. But the current at time 0 is in fact 0. So let's see what we get here. We're evaluating from 0 to TF and from I0 to I of TF. All right, let's plug in the bounds. On the left-hand side, just T sub F. On the right-hand side, we have the natural log of what we get when we plug in the upper bound minus what we get when we plug in the lower bound. All right. The rules for logs: the subtraction of two logs is the log of the quotient. Since we're in the charging up mode now, epsilon, or not epsilon, but EMF over R, that's the sort of long time steady state current in the circuit. So that's the current starts at 0 and is going to grow to that sort of asymptotic value. The denominator here will always be positive because we're subtracting the final steady state minus something somewhere less than that. But so will the numerator. So the absolute values aren't necessary. We can make this a just parentheses. And now we can exponentiate both sides. And we can sort of do away with the T sub F indication. Doesn't matter what we call it. It was a variable of convenience. Since, well, we can cross multiply and solve for the current as a function of time. We're done. Except for the fact that in this case, we know for sure that I sub 0 is 0. That's the initial condition. Right when we flick the switch to closed, there is no current flowing yet. It's about to change, but it hasn't yet. So with that simplification, we could even, we could rewrite and call me crazy if that doesn't look like the exponential asymptotic charging equation for a capacitor. As we build up current in the inductor, we approach a steady state current, just like we approached a steady state voltage across the capacitor plates. We could even define a time constant for the charging, for the building of current in a inductor, and rewrite this as exactly the same way we wrote the capacitor charging equation. The fact that the buildup equation for an inductor looks in an RL circuit looks so much like the buildup equation for a capacitor in an RC circuit makes me think that if we switch the story and remove the battery from the circuit, like let's say our initial circuit had an extra bit over here with a switch all on its own, and we close that switch at the same time we open the battery switch and remove the battery from the circuit. Now we just have the inductor and the resistor. The current is currently flowing in the resistor. As we take away the EMF, that current is going to try to decrease, and the inductor is going to continue to try to put it back as much as it can according to how much energy we stored in the magnetic field we set up. That current will eventually decay because we're spending the energy pushing it through the resistance. The discharge equation for a inductor, because the buildup equation looks the same, so the tear down equation should look the same as it did for a capacitor. It should have exactly the same form because we have exactly the same form of equation starting our differential equation. So we can, I think, just right by inspection, and I'll leave it to you to prove it sort of rigorously, that the current equation for tear down of the magnetic field is exactly what we would expect it to be. Okay, that's part 1 of 3. Okay, part 2. We are considering now a circuit with a capacitor and an inductor. Suppose we start the clock at some time 0 after having spent some time charging the capacitor. So the capacitor is initially fully charged with some initial voltage according to the EMF, the battery in the gray circuit, with a resistor. And suppose for a long time we had this particular switch closed and we were charging the capacitor so that we had the positive plate on the left and the negative plate on the right. All right, so sometime later we open that switch. Whoa, I erased too much. There we go. Sometime later we open that switch. The capacitor still has its stored electric field. And instead, we close this one. Now, the stored potential difference across the capacitor is going to try to push current through the inductor, just like we saw in the RL circuit a second ago. The EMF is going to try to push current through the inductor, but the inductor is going to respond with the induced current that tries to oppose that. So it'll take some time to build up the current through the inductor. Once there is current through the inductor, however, we will continue, now that there is current, we'll be discharging the capacitor, and at a certain point, we'll end up charging the capacitor backwards. Because remember, the inductor wants to try to preserve the current that exists. Once the capacitor starts setting up current, the inductor will happily perpetuate it. So the capacitor will end up fully discharging, and the current will follow around and will end up charging the other way. At which point the potential difference across the capacitor will start to oppose the continued current, and eventually we will build up the current through the inductor will decrease when the potential difference across the capacitor is as what it was just the reverse, and then back again. All right, so I'm setting up a sort of a sloshing story between fully charged capacitor and instantaneous zero current. And fully running current, maximal current, with no net charge on the capacitor, and back and forth. Let's see what the math looks like. I'm going to follow the convention of the Young and Friedman text for this and choose a non-conventional current direction. It looks like current flows the other way when the capacitor begins to discharge. It does. The potential difference across the battery will try to push current counterclockwise. But I'd like to consider a labeled clockwise current, because actually the relationship between current and the charge across the capacitor is inverse. When di dt is positive, when the current is increasing from zero, that means we're discharging the capacitor. So dq dt, the rate of change of charge stored on the capacitor, is negative. And that backwardsness is accounted for in the sort of non-conventional choice for the current direction. If we follow the current in a loop from A to B and back, our Kirchhoff equation for this circuit, we have the voltage across the capacitor, which is negative. As we go from the positive terminal to the left, that's a potential decrease. As we go through the inductor, as labeled, now the current passing through it, the inductor will try to oppose that, and we end up with a negative L di dt. And again, the odd choice of current direction helps explain the fact that both of these terms are negative. Di dt has a relationship to the potential difference across the capacitor, because I'm planning to express that potential difference in terms of the charge, the instantaneous charge stored on the plates, and its capacitance. And the backwards current is tied up in the fact that as Q decreases, I increases. So there's an odd relationship there. And again, this choice helps resolve that oddness in a way that ends up yielding results that match empirical data. Once that sort of tension is resolved, the rest is straightforward. The current is, by definition, the rate of change it's the passage of charge. So we can express the instantaneous current as the rate of change of charge on the capacitor. As those charges move through the circuit, the capacitor discharges. So that means di dt is actually dq squared. It's the second derivative of charge. There's no reason to preserve the minus signs anymore. They were physical, but now we're talking algebra. So let's make these both plus signs. And let me write that again. And as we consider this rewrite, I'd like you to think back to 231. When we considered the oscillation of a mass on a spring, we wrote that actually, when we considered oscillation, physical oscillation of any kind, we said as long as we can say that the acceleration is proportional to the negative displacement. That's oscillation. As long as we can say that the acceleration is some constant times the displacement and negative, there's a restoring force, we said, when in 231, as long as the second derivative of the position is negative proportional to the position itself, that's oscillation. This relationship we wrote for the LC circuit has exactly the same mathematical form, which means exactly the same mathematical solutions or mathematical equations will be a solution for this differential equation, which means we can just write it. This is a sinusoidal relationship with omega squared angular frequency related to L over C. It's here. We're done. We know that Q as a function of time is some amplitude times the cosine of omega t, where omega is the square root. Oh, wait a minute. I've done the algebra wrong. Hold on. We subtract Q over C and then we divide by L. It's not L over C. I apologize. Let me go back and fix that. The proper color here, this is 1 over LC. So I've got to fix the definition of omega, 1 over LC. What should the amplitude be? Well, we're talking about the function that represents the charge on the capacitor. The charge on the capacitor is originally expressed in terms of the capacitance and the potential difference that was used to charge it, which was the EMF of the original battery. So we could express the amplitude as, let me use this color, C EMF cosine omega t. If we wanted, as we found for the RL circuit, a function for the current as a function of time, no problem. We can happily take a derivative with respect to time of that thing we just wrote. And again, we see that the sign difference is baked into the math now that we made our initially unconventional choice. Everything that we said about oscillatory motion, we can say about this. Q is our analog here for the instantaneous position. The current is our analog for the instantaneous current. uh, the instantaneous velocity of the particle in oscillation. If we took another derivative, because the inductor is interested in di dt, we would end up with something that is negative proportional to the original charge on the capacitor, which is exactly what we said in the first place. All of the energy considerations of oscillation are baked into this solution. Uh, yeah, that's the story for an LC circuit. All right, one more part to go. Let's consider, for the third part of our introduction, a circuit with a resistor, a capacitor, and an inductor all in series. Initially, we spend some time with the switch in this configuration charging the capacitor to an initial potential difference, EMF. Let's label that EMF, so that the initial charge on the capacitor is, like in the previous part, the capacitance times the EMF. Then at some time 0, we close the switch this way, removing the EMF from the circuit and allowing the capacitor to discharge through the resistor and the inductor. Let me label these things: capacitance, resistance, inductance. And as we did in the previous part, let's choose the direction of current to be kind of contrary to our expectation, so that we've baked in the negative relationship between the charge on the capacitor and the rate of change of the current. All right. Assuming we do that, we can write down the Kirchhoff loop in the direction shown, kind of by inspection at this point, because we worked through it a second ago. If we start from, let's start from the corner here, I suppose. Let's call that A. We'll go to point B. And then to see a Kirchhoff loop for A, B, C, A gets us the following relationships. The current passes through the resistor in the direction shown, so that's negative IR. We're backwards the labeled conductor voltage, so minus Q over C. And again, in the direction of the labeled current, the EMF across the inductor is opposite, so that's again a potential drop, L di dt. And we're back to A, and that's going to be 0. As we did before, there's no reason to keep these minus signs. They were physically meaningful, but now we've got just an algebraic relationship. And now we have a differential equation that we are maybe not as familiar with the solution for. The textbook that you have might present the solution. We could adjust the differential equation written here so that it looks a little bit more normal. Let's express everything in terms of the charge Q. Then we have L d squared Q dt squared plus R dq dt plus Q over C equals 0. And we see that this is a second order differential equation in Q, but not of the kind that we already know the solution for, as we did in the LC circuit. Maybe we have seen the solution to this kind of equation before. And in fact, if you're working from Young and Friedman, we can write down the answer. because they show it to us. And if that is shown to us, we could, in fact, take two derivatives and show that it does, in fact, satisfy the equation in magenta. But I'd like to spend a little bit of time on Thursday developing a method by which we can convince ourselves that this is, in fact, the solution for an RLC circuit. That is the introduction. The stage is set. Thanks, everybody.